Good afternoon, everybody. Now we are starting the long-waiting debate. We have been looking forward to this debate whole day. And my name is Guangya. I will be the moderator for this debate. I would just like to start with some context of this debate. Half a year ago, we started to put a conference program on the resilience topic. And at that time, it was not as urgent thing as today, especially after the blackout we have recently had in Spain. And as you know, like power system is undergoing fundamental changes, and we have more and more renewables in the system, growing on a rapid pace. And we also have a decarbonization of transport, heating, and so on. And that put electric power system at the center of the energy system. So electric power system should be the last one to fail in a way that if we want to continue this decarbonization. But the resilience of power system has not been so much embedded in the daily operation and planning in the past. And then in light of the recent blackout in Spain, and also like we have more and more decentralized operation of the DERs in the power system. There's more and more challenges on this topic. And today's debate is mainly to explore those challenges and then leave a message for the future. So before everything starts, let me give a very brief introduction to the high esteemed panelists. We have, first of all, Professor Bikash Paul from Imperial College London, leading expert in power stability and control with more than 25 years of research in this area. And I've got many of you familiar with his work on power system dynamics and control. And then we have a second panelist, Professor Jakob Østergaard, who is head of Power and Energy System Division in the DTU Wind, DTU Wind and Energy Systems Department. And he has been a key voice in the energy system area in Denmark, has been frequently been invited to interviews by journalists and also address the parliament. Welcome. And then we have also Dr. Johannes Stockel from Austrian Institute of Technology, has been head of Power Electronics Group. He has a different background than other panelists who is from a component hardware background, but he also been working with the component control, especially converter control in the past. So welcome. And then at the last, we have, not last, but here, like physically, we have Johanna, Dr. Johanna Wowek, who is an assistant professor from DTU Wind and Energy Systems. And she has been working on the AI application in power systems in the past few years. And then online, we have a true pioneer in power system research, Maria Illich. She is a professor from Massachusetts Institute of Technology. And unfortunately, she cannot be here physically today due to other obligations. But it's very nice to have her online with us for this debate, because her opinion on these topics will be highly valuable for all of us. So today's debate, we will organize in several steps. So at the beginning, I would like to invite all the panelists to give some opening thoughts about power system resilience in general. And then afterwards, we will have a few moderated questions from the panelists. And at the end, we will open up the floor to the audience for comments, questions, and so on to the panelists. So, Professor Bikash, we'd love to hear from you some opening thoughts. How do you see power system resilience evolving in the next decade?
Thank you. Yeah, this is It has become an ever sort of important topic. We started with stability, then it became reliability, then it became resilience, but still all three of them are there. And I fortunately work in stability field, so there is always a lot of things to work on in that. Before this, about an hour back, we received this email from the MSCA on the first preliminary investigation report on the Spanish and Portuguese blackout. And you see that the triggering event, final triggering event that disconnected Spanish system from the French system was a 400 kV transmission circuit failure on loss of synchronizations. That side was 48 hours on Spain. So this is essentially the protective relay worked. So out of swing protection. So that's the protection worked, but system is not resilience. And then we are moving more towards new generation technologies. In fact, we have moved, right? But all our philosophy of interconnected system was on the basis of large synchronous based generations, because they are all at the remote location where we had the resource, coal or hydro. We had a long transmission line, we had the only transient stability problem. But now we are all distributed sort of generations, wind, solars, and many other form of generations. So these locations of generation have changed, and the demand also has changed, but we are still with the AC system, right? So that is where actually the resilience has been challenged, right? So we have moved more towards non-synchronous generation. We have moved towards more converter interfaced demand, but we have that still the AC system. So how the system which was designed to be reliable on the basis of large synchronous generation and passive demand would actually remain resilient when both ends have changed, right? And then also the other things like their control technology, and then more and more say proprietary information, like we do not know much about the power converter inverter. Today's talk was how many papers did not mention grid forming converter. It's easy to count then, how many papers mention that. So this is essentially resilience is really is very important. And what we need actually, we need a solution, but power engineers cannot do. Yeah, we need to have more like AI experts and other data scientists and so on. And most important thing is this, I may sound a bit pessimist, but we need to actually disconnect the people on markets from the resilience thing, okay? Market does not deliver the resilience, The people come with a grid in the market. Anyway, I better stop.
Yeah. Well, actually, one of the challenges it is the decoupling between the market and the physics of the system, which is given a challenge. But we need a new way of operating. That's for sure. Okay, on the same topic, I would like to also ask Professor Jakob to share your statement.
Yes, first of all, thank you for the invitation, and it's a super timely event. Not only the topic of resilience, but also the focus of this project, InnoCypes, educating the technology leaders of tomorrow with a large number of PhD students. And what I would actually like to just very briefly mention is that these two topics, resilience and education of the future technology leaders, are actually two of the cornerstones of our department's new strategy. We have four new focus areas, and these are two of them that we're actually addressing here today. But of course, it's evident that resilience is a very, very important topic. We saw what happened in Spain that reminded us. For me, there's the two big areas that we have to consider, and that's the new properties of the system. Biscas mentioned some of them. That will introduce various vulnerabilities for the system. So that's the kind of the one side. The other one is new threats to the system. It's a new world we're living in, digital world, also with countries that are perhaps not want us all the best. So we also have to protect us in new ways. So perhaps we can discuss some of these topics during the session. Yeah.
Thank you. Thank you, Jakob, for your comment. And then next, I would like to invite a comment from Johannes on the same topic.
Thank you as well for the invitation. Yeah, the power system in Europe has to deliver currently like 3,000 terawatt hours a year in Europe. So we will see more than 5,000 terawatt hours, something 2040. The electrification of the society will mainly be driven by power electronics converters. And there we see that we are going further that path that was already described by the two speakers before. And yeah, we have to prove the resiliency in a system which is mainly converter-based further. And we have seen today in the talks converter-based mainly from the HV side. But we know that, for example, PV is a lot in fact on the low voltage grid. So we have new opportunities with power semiconductors also for higher blocking voltages, 3 kilowatts and beyond, kilowatts and beyond. And we explore medium voltage a lot. And this brings also opportunities. We have to make use of these opportunities in the near future. We have to define. There was already the first talk today with respect to standardization of grid forming capabilities, etc. This has to be done at some stage so that we can really make use of the new opportunities we have with fast transient technologies, which can act much faster than hydropower, for example, in the grid, that we can really make use of the benefits and not fall into the trap of disadvantages.
Thank you, Hannes. Now I would like to invite a comment from Johanna on this topic.
Thank you. Also from me, thank you for the last minute invitation, Guangya. I think I agree with most of what was said before, and would just like to maybe share an observation. So I'm not really a resilience expert, but what I see is that in our planning and also what I see in research, we're quite in our own areas, and I think it's essential that we start thinking the system a bit more integrated, so that, for example, that when we're doing operational planning, that we're considering stability. This is happening more and more, but I think that, and especially then AI, I think we will talk about this a bit more later, can be an enabler to do this linking from actually daily operational planning and considering stability, and also consider how different uncertainty travels through those stages of different planning. So I think that's also an interesting aspect to consider.
Thank you, Johanna. And then Maria, we are also been looking forward to have your comments on this topic. If you can share some of your thoughts.
Good afternoon, everybody. I'm really sorry I couldn't make it. There were some other time conflicts, but I would have loved to. I think your program is great, the project. So, and I look forward maybe later in the year to actually spend some time in DTU as we were planning. So, well, it's I've been in this for a very long time. I'm getting old. And I've seen it, and I've taught at many places, but I would say that what happened now in Europe should not come as a surprise. You know, if you really think about what we know, what we don't know in the how to operate interconnected systems, you very quickly recognize that protection, control, things that are needed, including IBRs and power electronics, things that are needed to enable flexible, fast operation to very fast evolving problems, has been not that developed, I would say. There are people who come from the hardware side, they integrate things, but the rules for control and protection so that the system level performance is somehow predictable, even during faults and fluctuations now as we have wind and solar, don't exist. We don't have transparent protocols for controlling fast power fluctuations by means of next generation IBR controllers. That's the bottom line. That is on the very fast time scale. I just want to say something more about the resiliency because I have been involved now for 2-3 years in Puerto Rico, where, if you remember, they have these hurricanes and you have one power plant goes out and everything goes out. This cascading is unbelievable fast. But if one looks into, this is going back to Johanna's comments on planning, if one looks back into actual time scale over which things started deteriorating, you can see that sometimes there is several hours from the time the first large piece of equipment fails till you come into very fast collapse type things. So it is possible. It's a very interesting challenge between how much you can predict conditions, how much you can schedule what you can schedule ahead of time to utilize what exists. For example, in Puerto Rico, some national labs are working on predicting, because of the weather, what pieces of equipment are going to fail. And if they fail, now you have different scheduling things, AI, machine learning, some people are working on that, predicting, optimizing what other controllable equipment to adjust so that you actually localize the effect of the first outage so the cascading doesn't happen. So one of the huge challenges, even before you get into very fast time scale, is how do you localize the effect. We look into, I've seen, who knows, maybe 10 blackouts worldwide since, I've been in my career. Each one starts with either one transmission line or one generator going out, and then the other ones get overloaded. And the link, very intriguing link, that's why people actually don't know what has actually happened in Europe now, is that protection malfunctions, things that the line that's overloaded, the next line is actually faulty, disconnects that, and all it goes. So we don't have good prediction tools. We don't have good scheduling tools for adjusting during that time when you actually have time to adjust something in anticipation of bad weather or losing some piece of equipment. And then the automation for protection and control really need to be revisited. So just one comment on connecting on IBRs. All the IBRs, to the best I know, they're local and they don't cancel the effect of inter-area oscillations. So just something to think about. So I'll stop here and we'll keep going later. Okay. Thank you.
Thank you, Maria. And since we are on this topic on Spanish blackout, and we would like to start with the Danish because we're now in Denmark, and Denmark has a similar system as Spain in the way that there are also high renewable penetration. So I would like to first have Jakob to answer this question, that what is your opinion about this blackout in general based on the public information we have right now? And how far, do you see that Denmark will have a similar situation as Spain? And what we can do to avoid this avalanche kind of blackout. Yeah.
Yeah. Yes. Yeah. Thank you for the question. Yeah, it is actually limited information that is available at the moment. But there has been shown several measurements of frequency and some PMU measurements and so on. And I actually spent a bit of time just to look into it, and what seems to be a fact is that there were some oscillations taking place in the system with a bit less than 1 hertz period time, about half an hour before the event with a total blackout. And these oscillations died out, and then 15 minutes before the event, other oscillations occurred with a bit even lower frequency took place before the last, I think, 5 seconds, where there was a cascade of plants disconnecting and the last frequency drop and decoupling of Spain and France, leading to more than 50 million people without power for many hours. But these kind of information do not say anything about what was actually the root cause of this. What was the reason, and what was the result of the event that took place? So what is actually needed is to do a comprehensive analysis of all the measurements that are in the system during the event, and I know the TSOs are working heavily on that, but it will probably take some time before it's billions of data points that have to be processed before they can probably come with a final conclusion what actually took place. But I think, despite that, I think we can actually learn things or start to consider, because I think it's a reminder about that we have to protect the system against these phenomena, and as of course renewables has come in big time in the system and changed the behavior of the system, adequacy of the generation becomes much more important. There's also some couplings to the market, but perhaps we can cover that later. And then, of course, all these units being power electronic connected gives much faster dynamics, where we need to dive into EMT-based simulations and so forth to properly understand the phenomena. But I'd also like to mention that it's not only about power electronics; it's also like extreme weather situations. To understand those much better, we design the system against N-1 random errors, that are faults that take place in the system, but weather phenomena are not only affecting a single component; they can affect a whole region. And the same goes with cyber attacks or physical attacks that not necessarily is a single event taking place independently of rest of the system. But at this point, I think we should be very careful on blaming the renewables. We don't know yet what the root cause is. There's nothing indicating specifically that the renewables was the root cause, and actually what I think we should have a focus on is to make sure that the way we protect and ensure resilience of the system follows the development we have in the system and the threats. and where we perhaps has lagged actually behind, and we need to update all these ways of managing the system to follow the development we see that take place in this very high pace.
Thank you, Jakob. A following up question on this would be that there are also, like for example, RTE is connected to Spain, and then there's a disconnection between French grid and the Spanish grid during the blackout. The reason we don't know yet, and but there's also let's see some discussion. For example, like Norway want to maybe stop the interconnection with the Denmark, at least renew 2 of the HVDC connections by the next year, and because they see that the interconnector will increase the electricity price in Norway. So how do you comment this? So because this is a question also linked to, for example, Denmark, the resilience of Danish power system, where if we in the future that we lose some interconnectors to the external systems, how should we prepare for such scenario?
Yeah, I think this case with Norway is quite interesting, and also something we should really try to avoid. We all benefit from an interconnected power system, and we see these tendencies towards what you could call energy nationalism. Also Sweden, they didn't want to invest in interconnector with Germany. And actually it's a huge benefit for all of us by having an interconnected system and an interconnected market. I've seen numbers of that the European electricity market and interconnected system generate a value of more than 30 billion euro per year, and we'll lose that if all countries try to solve the energy supply independently of each other. So it's super important also from an economic point of view that we actually have an interconnected system, and then of course it's also benefit the reliability of supply and the resilience of the system. So this is really a development that we should be careful about.
Thank you, Jakob, for your comments on this question. And I also would like to hear from Maria. Let's see what we could actually learn from this blackout, and then your general opinion on this, and also any recommendations you have.
So we've lived, as I mentioned before, we lived to many of these.
Okay.
You know, it's good to look at statistics actually, and to recognize that we don't have. I want to talk to young people about this. We really don't have methods for managing systems under abnormal conditions, to controlling, to automating, and so forth. So these methods have evolved over time in sort of, I would say, mushroom level, including the problem that Jakob was just talking about. The seam in America, we call this seams problem, when different areas, New England and New York, don't collaborate. And so the minute you start thinking about the entire Europe, just look from the newspaper, it looks so complex. Nobody knows what is the cause and what is the effect and so forth. So what is missing are some systematic protocols for collaborative operation of the system under different conditions, and inside different areas, inside different countries. You have also protocols for understanding when some large solar or wind power plant wants to connect. You want to understand what are its interfaces and ability to respond to the system conditions under different conditions and so forth. So the story is very long. We do not know how to test these new technologies. When you put them on the system, you get actually say, okay, this IBR is doing its job. You put it on the system and it doesn't do its job. And we have, I think, pretty highly paid Department of Energy project called Unify, in which this is the key question. You know, if you want to integrate a lot of renewable resources, can you actually design the interoperability so that interoperability is a very big question, and the term used in Europe, in US now, make these components interoperable. Think about having enough automation internally themselves to collaborate and manage interactions with the rest of the system. At MIT, we have several students working on that. How do you actually, in Europe is a little different, but automatic generation control, people are familiar with that. It works beautifully because each control area and each state has the rule that they are going to adjust themselves so that they cancel the effect of ties, the interconnections with deviations from what was scheduled with the rest of the system, and deviation imbalances caused by their own deviations from what was predicted. So that area control error that we use in automatic generation control really has to be generalized for faster time scale, for embedding, getting to have groups of IBRs actually behaving like AGC-like control area with some provable performance. So long story short, the root cause really doesn't matter. If you look at 2003 in Ohio, and then you get all of the loop flows and circulation throughout the entire northeast of America, cascading and so forth. This is what happened here. So it's nothing new. But so it's not just about IBRs and renewables. It's just there is no system in place to manage to localize first over a slower period of time. When something fails, to localize its effect by rescheduling controllers, set points of controllers, everything, generator voltage set points, adjusting real power, doing load shedding in much more better way than we do it now. And then as time evolves, just having automation to cancel the oscillations between the components and between the areas. This is huge opportunity and challenge for the dynamical systems, complex dynamical systems, where you cannot think about it just as one monolithic system in which something can happen and I can just fix it or not. So it's a huge opportunity, I think, for young people to rethink the problem. And at the end, I think things are going to continue to happen unless we fix control and protection. So I'll stop here.
Thank you, Maria. I think since we touched, now we are on this topic about stability and control and protection. You know, in all the blackouts, protection is playing a kind of role that is seems not that is correct, because let's say for example, this Spanish blackout, we lose the system in 5 seconds, something, and this kind of speed only protection could actually collapse the system so quick. So and in history also, in the history of blackouts, it's the same. For always the protection start to disconnect and so on. We have the cascading failure. And then with this, now I would like to actually come to this question about protection control topic and also link to the stability. When we have the converter-based power system in place, and then now for Europe, since we have already so many converters installed, there's no way that we go back to the conventional power system based on synchronous machines anymore. So we need to look forward and then to solve this problem. And what are the challenges you see in this area regarding control, protection, and also stability of converter-based power systems? I would like to invite Bikash for this, because due to your experience in this.
Yes, control, stability, protections, I'll touch upon that. But I would like to pick up from where Maria very nicely touched upon that interoperability. So some of you know that this time you received some message from me that I'm standing for IEEE Power Energy Society President position. And one of my vision statement has been that all the standards that is being developed, say you take about P2, P28 hundreds, about the dynamic voltage support from IBRs and so on for the system. So these standards, etc., they are very much focused to say certain region and certain type of technology. So that is where actually the interoperability comes, that where different standard developing entities in different parts of the world, we really need to work together. So that's why I was saying that, if you vote for me, okay, it's not my election campaign, but that was my statement that, I need to bring in SIGRE, PS, IC all together to make sure that all the standards that we develop, they are interoperable, and then, they can be really truly technology neutral for, these sort of things. Now, coming back to this protection, control, and stability. Now, if you look at as you said, the history of all the blackouts, it's always saying that, the protection either did not operate properly or it misoperated or something like this. So why all these things are happening? Like we have only two routes that to trigger this, either oscillation or angle instability or stability, or most of the cases some voltage instability kind of thing. That's the history of the anatomy of this. Even the one in 2019, 9th August in the UK, that was again, the Siemens Gamsa investigated that again the voltage control issue of the Hornsey wind farms and so on. So it is the voltage and also it is the angle. That means we are still in the synchronous systems, but we kept the transmission part that way, and the generation on the synchronous side is dropping. So who would provide you the the independent reactive power support was the synchronous generator. So they are disappearing. So naturally that has to be provided by all these new technologies. So how they are fast, as Jacob said, but are they able to provide? Are the technologies, etc., are standardized or resilient to provide that? This is this. The other aspect is that more and more we are going for demand, which are having more and more power electronics. Now, that for power electronics type of demand, they tend to be more and more constant power type of demand. So any voltage issue happens, so they would continue to draw more current to match their power. So you have the stability things. So we honestly do not know why and how the protective relay between on the line between France and Spain operated, but I can tell you normally this type of distance relay will have 3 zones: zone 1, zone 2, zone 3. We also saw something. Usually the zone 3 is having a bigger reach, and there are always that issue of load encroachment and out of swing, that type of thing. So given the demand side has changed, given the generation side also has changed a lot, we need to see that how much this protective relay systems and their operating philosophy also have had to catch up with these sort of changes. So that is where actually the true effort should lie, this protection. Then only we will be able to see that, okay, so that means again it brings us back to the protection, control, and interoperability. So that is where actually the focus should be. So but these oscillations are now becoming of higher frequency, so not anymore less than 2 Hz. So EMT model is now must, not a phasor model. So that brings us back to again Jacob's point and also Maria's point, new tools, how we are going to do. Many of these power converters model, etc., we do not know. We have been seeing some impedance model, but that is again very simplified. If on the MMC, multimodal power converters, how the controls are configured, we do not know. And with time now, we now have there is no gap between protection and control. Yeah, in terms of mechanism, in terms of this time thing. So it's a huge challenge, but at the same time, it's a great opportunity for, to work on that. So model, data, and design planning. It's very important. One thing that has not happened is the investment in the power transmissions infrastructure. See, if you look at that, the way the demand has grown, the way the technology has changed, but our main infrastructure like transmissions, transformers and all, there we did not have enough, because there you need to have solid money. So this is where we now again need to see that what kind of market and economics mechanism that we have, which really encourage, or which really should not ignore, that we really need to invest lots of things on the hardware. Software is fine, but hardware has to be also quite strong, or quite enforced to do that. And then the tools, control and protection tools, prediction tools, fast dynamic security assessment tools. So these are actually the area for us to pursue. I think I have spoken a lot, but I'm sure actually that this is a very complex problem, and bringing again the economics into the operation of such a systems with so many technologies in place makes the understanding of the problem even more complex. So that's why I'm saying that for the time being we could park the idea about the market for a couple of years to make the problem at least understandable relatively easily, because moment you bring market, etc., it becomes so complex, people even don't understand what's going on. So that is where I would like to see this.
Thank you, Vikash, for your comment on this. And then when you mentioned about the transmission asset expansion, investment, that is to also improve the synchronization among between the systems. And then on this topic, I think one of the technologies we discuss a lot today is the grid forming. Right now, we have the grid following, but then when we have more and more converters in the system, the grid following cannot work together, because they are the system. So when they are the system, we need first to build a system for them to follow. And therefore we have this grid forming that seems now is a promising technology for the next step for the converter control. And I would like to also then have a question on this topic, because we have actually started grid forming maybe 20, 30 years ago already, the research. And then it's still, we don't see much progress commercially from these projects and so on. So I would like to ask the question to Johannes, since you have been in this area for many years. When are we going to see the first grid forming technology being deployed in the system? What are the barriers for this technology? If you can give your opinion on this.
Thank you. As you mentioned, many years of research. Firstly, I think that the implementation comes with the technological possibilities. Looked it up previously, that the IGBT, which is like a standard device, has a patent from 1990. So that's not that old. So most of us are older than IGBT, or many of us. This was the enabler for solar power, for example. And so the rise of technologies and the integration in the grid comes with the availability, the production, the scalability, etc. So when there is no need, then there is no implementation in the field. The results in research are, I think, very well found. There are many possible ways of implementations. There are implementations on different levels. So when we say grid forming, is it grid forming on transmission level, grid forming on medium voltage or distribution level, as well as low voltage? Because I mentioned this before already, so we have a lot of generation which comes from lower levels to transmission. So grid forming then in the future might not fully be seen with this title of the crystal ball. So I will bring this also in there. So what will be the consequence of this grid forming converters? potentially, is that we will be maybe able to decouple in case of emergencies from higher levels of grids and be self-sustained, which can limit the area of influence. Maybe one word to the blackout as well, which I want to add, because we see the root cause and so on, but I think we should also see that the grid was functioning well quite fast. So the people who work for TSOs, they're training these events very often, and this 1 day maximum is like of a target, and it was like 10 hours or something like this, which is a success, I would say. Also there was of course this blackout before, but in the near future we will see, and I've seen this in IEEE from yet spectrum, that we have issues with the production of high voltage transformers. There are longer lead times that we expect, so there's a global shortage of these kind of transformers. We see for distribution transformers, medium voltage to low voltage, that the break even for solid state transformers is very close because of increasing copper prices. So more and more power electronics will be just the case, as we also need it, and therefore the grid forming will be there very fast. Also, add it again, the standardization there is, in my opinion, not there yet. So we need to define what we want to have as a system behavior of the individual component behavior.
May I follow up with this question with you, Johannes? So how do you see like this grid forming will start from distribution grid first to transmission, or from transmission to distribution? Which one you see that will take place earlier?
It's the question how far big the distribution grid needs to be to call it grid forming, as a self-sustained, because every household can do already its small grid. We do microgrids for many years, and this is already grid forming implemented. What we also do there, of course, we don't want to have self-sustained islands. We need to, and that's also already like the research is there, and also implementations are there to be able to be grid following, so that the transmission line is still the one who gives the pace. But in the case of an event, we can decouple, we can grid form, and then couple again once the power is established again on the higher level. So this is, you can say, this is already available. However, we could see that also the grid forming capabilities on offshore wind and on wind power are already on a late stage, and I would say that a few years or maybe sooner this is already there as well. So I would be very optimistic, I would say.
Thank you very much for your, if there's any comment on this.
Can I make a quick comment?
Yeah.
I just to what was said now, I think there is a huge gap between power electronics people and power systems people. I think we really need to create some challenge problems of when we make the statement that grid forming thing works well. Let's take the situation that we had now in, during the blackout. Is the control, and I have the whole thing here, don't have time to go over this, is the control sufficiently adaptive, sufficiently collaborative with the rest of the system so that it helps? We do not have that, and I just very quickly, please correct me if I'm wrong, most of the control for converters, IBRs, is, okay, I have droops for QV, I have droops for P omega, and then I emulate what the generator does, and I will tune this, who knows how, outside of context of what the system is supposed to do. I don't know what oscillations are happening on the system. This is a huge disconnect. It's really an opportunity for us to put ourselves together. So people design the best thing, they design the best transformer, the best, GFM, but then when you put it in the system, and I mentioned already with this unified consortium, maybe 10 universities participate. You design, like you suggested, the best transformer, the best gadget. You put it on the system. You test it. You validate it, what it can do. You put it on the system, and it doesn't do that. It's this interoperability thing. So please, I would love to get the response to that.
Yeah, I would fully agree that there is a gap, and therefore I was mentioning the first statement and the second as well, the standardization. The demand, what has to be the functionality which has to be implemented, has ultimately come from the system experts, and it has to be in a way that it is, let's say, future-proof as well. So we have, like, if I think back, many standards or requirements, let's put it this way, of this 50 Hertz 2 issue, which we came up then that we realized. So it was implemented, then we realized that when every converter disconnects at 50.2 Hertz, then we run into similar issues we were seeing right now. So the standards were changed, troop controls, etc. Also for this, and this is a more complex topic to have grid forming than just like a disconnect. So as well, the ultimate specification or the ultimate standard requirements have to come from the power system experts in collaboration with the power electronics experts. Otherwise, this will not work. Yeah, I would fully agree. Yeah.
Yeah, thank you for this discussion. I think we have been discussing this issue about converter-based power systems quite long now. I would like to shift the topic a little bit towards digitalization. And one topic we cannot skip is artificial intelligence, and how AI would be able to transform or solve some of the complex issues that we have seen or discussed before. So I would like to have this ask a question to Johanna. And how do you see the opportunities we have and also risks we have regarding using AI in a safety critical system like power systems?
Yeah, thank you. I'm very happy to answer this question. Let me maybe start with that the opportunities are really endless, and maybe that's also what's the difficult thing about it. During the last PSCC, so Power System Computational Conference, I think almost every second paper had something with machine learning. It's like the new optimization a bit. So my first comment is that I think that we really have to think about what's the reliable use that we can have and where do the applications actually make sense. Generally, if you think of neural networks, what they can do is that they are a general function approximator, and they can actually help us solve problems that we haven't been able to solve before, or they can help us solve problems faster where conventional solutions are slow. And so one example that I find very impressive is one that I saw during my time in Melbourne. They were developing this data-driven tool that was running power flow equations, and this was trained on 3 weeks of operational data from measurements. And this tool, with just 3 weeks of training, was more accurate than the most detailed model that the grid operator could develop. So this is just showcasing this huge potential that we have for system identification purposes, for example. This can also go towards faster timescales. I mean, we have a couple of researchers in our group looking into developing these faster timescale models that can be used for time domain simulations, also EMT simulations is what we're currently working on, to enable that we have this real-time simulation of larger systems, which currently is not really possible in the system. And that goes a bit beyond, I mean, the classical answer to this is the forecasting, so this goes a bit beyond that. In the forecasting, I think what's very interesting is, and one thing that I want to look into myself a bit is trying to anticipate and use the pattern recognition that AI offers to try to anticipate when a blackout could happen and what could be potential mitigation actions that you could take as an operator to suggest such actions to avoid difficult or dangerous situations. And I think that is an avenue also for AI that is a promising one to evolve. But then, of course, there are risks with it. One big one is the overall reliance, I think. So you really have to be responsible in using it. You can't just train a tool and then use it. There's bias in it. You need to be careful about which data you're using to train it, that you're not using, for example, that you're not using a stable system, so then you won't be able to predict an unstable system. However, we are expecting, and this is also not yet proven by research, but we are expecting that they are somewhat a bit less prone to uncertainty because they have this variability inherently inside of them, so that they will probably respond better to system uncertainty when you use them, for example, to solve optimization problems, which then could help a bit with the cybersecurity aspect and when you think about bad data. But of course, I mean, all of that is relying on the data, so the data needs to be trusted. And then one other big challenge I would like to mention is also something that we've been working on here, is that there needs to be trust in these systems and solutions. So, I mean, now we have the EU AI Act, which is outlining what responsible AI means for safety critical systems, which is the applications and power systems that we are interested in. But then it says, okay, they need to be explainable, interpretable, but we don't really know what that means and how we quantify that for our system. So that's a big open question. And hopefully the answers to that will help system operators and other stakeholders to actually use such models. We are now involved with the AI Effect project, which is a European project where we're building a testing experimental facility, also here at DTU, where we want to have this pipeline of where we can actually verify and get performance guarantees for how well specific AI tools can do. So yeah, I think the key is that we're really looking at the reliable use of AI where the applications make sense, that we keep looking and also keep collaborating or start collaborating actually with AI people. Because right now we are lacking a bit behind of they are publishing something, we are thinking about how can we use it, so maybe an integrated approach there might be nice. And then helping the users to actually trust it, so then when you have such a tool, for example, you have a human in the loop AI in the control room, the operator in the control room needs to be comfortable and they need to know how to use it. I think that are my key points.
Thank you, Johanna, for your comment. Now I would like to open the floor to the audience. If you have any questions or inputs to the questions we have discussed or the issues discussed. Yeah, please. Please state your name and.
Sure. Yeah. Simon Tindemans, TU Delft. I'd like to actually continue something that Johannes mentioned something about this. So the other side of resilience is, not just making sure the system doesn't fail, but also how to get it back up again, right? And that went well. And I might argue that actually having this seams in the system, which makes it very suboptimal, has helped here, right? 'Cause it was a clean cut. Spain and Portugal were off, and then the rest was up and running, and they could quickly help reconnect, right? There was all stories about black start that would take days and so on. And of course it doesn't, because you can just, grow the grid from where it was already working. So my question, I think, to the panelists would be, to what extent should you purposely try and be suboptimal? And how can we convince people that maybe a suboptimal grid sometimes is a good thing, if we're talking resilience? And maybe riff off that. But
so who would like?
Can I take a crack at that?
Sure.
Okay. So it is, that question came up when the electricity markets in the Northeast were created. So the Federal Commission wanted to collapse New England, New York, and Pennsylvania, huge area, into one market for efficiency. And some of us, I have a startup actually, which started that way, to show that really what you need is to give enough autonomy to individual sub-areas to decide how much they want to trade and exchange, and then have minimal coordination, at least by one of those markets, to say, okay, out of all of these things that people want to trade or exchange, help each other. This is the optimum thing for the entire area. And then give that command, people, the sub-areas readjust. So it's very interactive. It's not either just top-down or completely decentralized for suboptimality. And you can show that way that you are almost near-optimal. We ran the entire Northeast, several times. It was going on for 5 years. And so it's not either or else. You can do both. And so maintaining enough autonomy to different areas. And right now we are seeing, I don't know if I want to mention this, but the country at war is you can deduce for yourself, is transforming bulk power system into system of interconnecting, interacting microgrids for security, because there is one single point of failure if you just have large grid and you have all these cascades. If you put DRs at different locations and they don't know, and they know how, and they have their own sub-objectives and know how to collaborate, then you are much more resilient. So I think that the system is really transforming sooner or later into system of sub-areas. You can call them microgrids, connecting, disconnecting, as Johan said, and or for different purposes, but there is this enough control at the sub-areas level and minimal interactions between the areas to keep everything together. And it doesn't have to be suboptimal. That's sort of answer.
Any other comments on this question from the panelists?
Actually, if the person has, you can send me an email. I'll follow up and send some references. This is a very important question, actually.
Then I would like to invite other questions from the audience. Any other inputs, questions? Yeah. Durian. Yeah. Please state your name and.
Yeah, sure. So my name is Durian, and I work for Siemens Gamesa. But just a question. I mean, we are talking about a lot about the Iberian blackout. How do you see the role of the regional security coordinators in this area? Because I mean, they can see pan country, right? So do you see that they should be more involved, or maybe have a different set of mandate than what they have today, or what is your view on this? Thanks.
Thank you. So, if any panelists would like to comment, or maybe Jakob.
No, but I think it's quite obvious that they play a really, really important role. The challenge of getting more situational awareness about the state of the system, and to be a kind of ahead of potential breakdowns is very important, and also to ensure the coordination, the problem that Maria addressed. They play a key role in this, so I'm sure you will also see a further involvement of their role in future. That's
Thank you. I mean, ultimately, a regional coordinator and their risk analysis, etc., are very important. Particularly, it again brings me back to the point that Jakob earlier mentioned about that interconnections have resulted a huge amount of savings, global savings. Like now, if we just become, as you're saying that way, that can we be suboptimal, or can we be really all kind of isolated systems and so on? So it's again brings us to that point of that at some point of time some area will be having more generation surplus, which would be cheaper, and compared to the other where there is a more demand. So there is no way that we could be looking in isolation. We have to be looking in integrated approach. That is, I mean, now you see that also in our whole geopolitics, there is always something like people are talking about their own country, own country. But it doesn't work like that because everything is now integrated. So the problem is a technical problem. So, I mean, all this blackout problem, I still believe there's a technical problem. So there should be a technical solution. Okay. And for that, of course, we need to have some policy and market issues and all that should support those sort of technical solution, be it investment on certain assets or on certain sectors. So I believe that, I would always prefer for, this, there are two equilibrium, Nash equilibrium and Pareto equilibrium. So you choose which one you want to go, I think. So it's the Nash equilibrium. So that overall, we have to have a global sort of benefit, not individual benefit. So that way. So that this is my kind of, understanding.
Thank you, Vikash and Jakob, for your comments. Any new? Oh, all right.
I have a very similar question to the previous one. Yeah, I'm Konrad. Nice to meet you from Green Power Denmark, also member of the InnoCypes project. I have a similar question to the one before, and we talked about contribution of grid forming from distribution grid. And my question is, do you think we need to have a discussion about roles and responsibilities in the future as well? Because at the moment, the TSO is mainly responsible for stability and system stability. But now if we see solutions and also possibilities in the distribution grid domain, do we also need to split this responsibility in the future? Is this part of the discussion today?
I think it is part of the resilience of the system topic. So, but I would like to invite panelists to give who would like to address this question from Konrad. Any of you? Jakob? Yes. Please go ahead.
I think you on something with this because of course if we pursue these solutions where you can go from an integrated system where energy is traded to a kind of emergency situation where you operate part of the system isolated. Of course, you then need to have some kind of transfer of responsibility and so on. But also in you could say in the more normal operation, a lot of the resources are actually located in the local grids. So there have to be a much stronger coordination taking place. And I don't know to which extent the responsibility have to be transferred, but at least there have to be much more coordination to ensure that we have a stable system.
Could I add something?
Yes, sure. Go ahead, Maria.
I think it's a lot of stuff going on. So standards versus protocols. People have tried, over years at different levels of TSOs, ISOs, or whatever to say, okay, every generator must for this and that keep its frequency within points, deviation from nominal. This number really does not make sense as a hard number, because it's more the question about the system operator or that level of aggregation, TSO or regional operator, really learning what are the ranges of capabilities that different subsystems can do in terms of ranges of even instantaneous power, ranges of rates of reactive power, and then deciding at the sort of coarser level if all these capabilities exist, what is missing? Should I add more storage or something like that so that I'm responsible for the system? To even make the justification, let's say if you have a lot of wind and solar, how much storage to put there? Well, that really depends on if wind or solar are controllable. So rather than just going to standards, and this has always been top-down approach, putting right numbers, working like tons of people working on what should be the standard, and then that standard is changing, is not applicable, using that standard for protection. So we have to get into much more interactive specification of different technologies, what they can do, but using common interface specifications. And these protocols that we are developing at MIT, they're exactly like that. Say, I have a black box, which can be area, can be region, can be inverter controller, inverter-based solar. The system operator or person in charge, entity in charge of coordinating those should really know just the ranges of interface capabilities that these resources know, and then do minimal coordination of those interfaces. It has taken several PhD thesis work recently, in the last 10 years, on people coming up with that. So it's actually very much the same as AGC. AGC, you do area control error, it's energy over 10 minutes and everybody manages that and frequency is regulated. Now we just need to move that to, Bikash was talking a lot about reactive power voltage. That has to be part of the spec on the interface, but also, the ranges, not every technology can do the same thing. They should not be required to do the same thing in order to connect to the network. And our standards will have been very, very rigid in that sense. If you are a generator, you have to meet these or else. I think there is much more flexible way, interactive way in understanding what different technologies can do, and then doing minimal coordination of these interfaces. That's what we've been promoting at MIT for a while in my group. So just.
Thank you, Maria, for your comment. Also, Jakob, for your comment. And for the interest of time, I would like to go to the next step. That's to invite all the panelists to give one statement as a takeaway of this debate session. So we will start from Professor Bikash. I'll start from there. Let's take a reverse order. Start from.
Okay. Thank you. Yes, I take some of these inputs, and as I said, I fully agree that we need to work more closely together, power system experts and power electronics experts, which also fortunately supports my point at the AIT. So we established this link between the planning and the power system planning and operations group and power electronics already. So it's quite an interesting topic. I also would have had a question actually for AI. May I ask this question? Yeah. Okay. So because the thing was, as not the power system expert, I was also always wondering for now AI seen as neural networks. There are lots of other, but neural networks. How much neural network AI can we afford in power systems control? Because we're discussing like this, what was the root cause of this, the blackout and so on. So that we do not end up with the question, so there was one weight of a neuron too much or less, and what's the consequence of this error? So how much AI can we afford in a critical infrastructure?
Yeah, I think that's an interesting way to look at it, and I don't have an answer to that. What I can say is that what we are doing now is that we're looking at it from the reverse perspective, and we are developing these tools that can certify and guarantee you what is the output range that you're getting for a given input range, so that your controller is actually only going to produce a specific gain, which also standard control theory would have said this is a stable gain. And then there shouldn't have been an issue with a single neuron, because then then once you have these, and these are actual mathematical guarantees, so we can actually reformulate a neural network into a MILP and then solve what are the bounds that what are the output bounds for a given input range that we are going to have. And then we have mathematical proof for how large this output gain is going to be. So then I hope that would somewhat answer the question. that we need to make sure that each single data-driven application is secure and safe. And these are especially these testing and certification guarantees that we need to develop.
Okay, hand over to you.
Okay, maybe we can. Johanna, maybe you can continue to give the.
And I think that just also makes my point. I think we need more communication among the different experts, like we've seen here. And sometimes reaching that level of understanding is a challenge, but I think it's worth the challenge and worth the try, because then we'll have better solutions. So that would be my takeaway for today.
Yeah, but then let me echo that and also bring, now market has been mentioned a couple of times and nearly concluded that that doesn't matter. But I will actually challenge that, because I also think that markets and the physical operation have to be brought closer together. I think in Europe we don't have a very close connection between the market and the physical operation, and I think we can actually learn quite a lot from US, where they have these nodal pricing solutions, where grid congestion is managed as part of the market operation. And we also have seen a case with Jalal, who was just passing by here a few minutes ago, with some of his research and with some of his students, where they've shown that by dynamically allocating reserves in the markets, they can actually improve the reliability of the system. If they allocate the same amount of reserves during the year, just shift them around a bit between the hours, so depending on the operational situation, they can actually reduce the frequency excursions beyond 49.9 with nearly 40%, just by modifying the way the markets works. So I think we also need to bring those areas closer together.
Okay, in one word, so it's difficult. My feeling is this: why is it so important that we have to operate with just plus minus 0.5% on the frequency? Can we then think about designing our gadget which would be more frequency variation tolerance, so that protection system can be relaxed? You know, it can operate between 49 to say, or 48.5 to 51.5 hertz. Can we think in that the direction? I mean, why is it so important that frequency has to be extremely tight? Because it's not that what I have never understood about this. But in any case, I think that, you know, interconnected system is one, and there should not be some kind of, you know, this division, like, okay, we in academia keep on pushing our own research and all, like you said, market dynamic resource allocation, but will the system would be able to deliver that? You came with some ideas, but this, so it's one power network, one energy systems interconnected, and we should all work together, industry and university. Then only we'll be able to understand the problem, and once we understand the problem better, we'll also be able to come with a better solution. Thank you.
Thank you, Bikash. And Maria, if you have a final statement.
Yeah, thank you. So blackouts are always opportunity for us. This is a strange joke, but it is true. We've lived through that. So I would say that if we are, one, to utilize large amounts of intermittent resources, and two, to utilize existing resources and the grid in a flexible, efficient way to deliver this power where needed, the opportunity is to extend protocols for managing real and reactive power imbalances over different time scales. End of the story. So the main innovation needed is how to control not just IBRs, but also all controllable equipment in a collaborative distributed way, like AGC areas are controlled today. Centralized primary control is too complex and communications fail prone. And so that is my suggestion.
Thank you, Maria. And then now I would like to give apparently the problem is complex, and we need also closer collaborations among the sectors and disciplines. And I would like to thank all the panelists for your engagement and your insights on this problem about resilience. And let's also thank you for audience for your engagement. And let's carry on with the ideas and the discussions we have from here to our work and beyond this room. Thank you very much.